projector and we can share. And
Okay.
it should be this. Hopefully you can see the introduction slide.
Mhm. Yes.
Okay.
Yeah, make it bigger.
Yeah.
You want it bigger?
Well, the print, it's okay, but it's always easier when it's bigger.
Yeah.
Well, let's see what happens at 300%. All right.
You have
All
to
right.
make the frame wider somehow. Yeah, that's better. That's easier to read.
Oh, okay. Don't need that. That better?
Yeah.
Okay. I'm not exactly sure why, but GR is, um, sorry, is usually thought of as being relatively difficult. And we'll see a little bit of it when we go through Riemannian differential geometry. And a little bit, well, we're also going to, just for completeness, we'll do Cartan differential geometry as well. But that one's going to be more complex. Lie groups and a whole bunch of other stuff that you don't have to know in Riemannian differential geometry. A lot of the things that happen in GR are quite mind-bending. But today we're going to just cover very simple, easy to understand ideas about GR. It is quite elegant and beautiful, and we'll take a look at the complete theory over the next year or so, I'd guess. Okay. No, that doesn't help. All right. One of the things, whenever you started in high school physics, you would learn about things like Coulomb's law and Newton's second law. And Coulomb's law, there's a coupling constant K. Then you have two charges, big Q and little q, divided by r squared. So using Newton's third law, the electric force is going to be the inertial mass times the radius, the second derivative of the radius r. And if you see the way that I've collected things here, obviously, if you're taking a look at the acceleration, you would divide by mi, and you get q over mi over here. And nobody would be very surprised because the units of this are mass and the units of this are charge. So no one would expect them to be identical. The inertial mass is the particle's resistance to acceleration. So we can do the collection that I said, and you'll find, as I said, Q over MI. Now, sorry. Okay. You could do the same thing with Newton's law of gravitation and Newton's second law. And when you do that, you have this term, you can collect it the same way. And that's equal to the inertial mass times the radius secondary, the acceleration of the radius. So the sorry. I don't know why that's not over where it's supposed to be, but I'm not going to fuss with it. If you did the same thing here, you'd of course get m sub g, which is the gravitational mass, divided by m sub I. And when even in high school, you're always taught that the gravitational mass is equal to the inertial mass. But there are two different kinds of thoughts about how the fields work. Man. Why did I do this bad? All right. Sorry for all the corrections here. All right. So the two concepts are actually quite different. One is the reason that you don't get acceleration used to a force, and the other one is the charge for gravitational force. So you are always taught that m sub I should be equal to m sub g, but since they're very different kinds of ideas, and not really well understood why they should be the same. So most physicists prior to Einstein just assumed that that was true. But is it really? Okay. If you do some different kinds of experiments, you'll find that there are some things that might be different ways of measuring the gravitational charge. You might consider just the number of nucleons not the binding energy. So the question is twofold. First of all, what's the experimental evidence? And second of all, where did we get this idea? Okay. Man.
Can I ask a question?
Sure.
Uh, there's no reason why the gravitational mass and the inertial mass should be the same at all, except that Einstein assumed it. And the reason he assumed it, I think, if you have a horizontal beam of light in an accelerating rocket, that beam of light will tend to bend. In the same way, if the rocket is stationary on the Earth's
You're ahead
surface,
of this. You're ahead of the story.
yeah, okay, I'm sorry.
Yeah,
But
you're
anyway,
talking about the equivalence principle, I think.
Right.
yeah,
We're
but
going to get there.
doesn't that equation, I mean, acceleration on the one part to the gravitational on the other? Isn't that,
Well,
doesn't that
that's
do it?
what the weak equivalence principles says. And but you need also, that's also an experimental question, not just a theoretical one.
Absolutely.
So there's been quite a lot of experiments that have been done over the years, starting with Etfish, who did it in, I think, into about 10 to the minus 7. But the most precise experimental test was done by the satellite microscope. And when they finished the mission, because they did it over time, they found that the weak equivalence principle was accurate to 1 part in 10 to the 15, much more than the Earthfish torsion bores that were done previously. And so the satellite experiments are the most highest that we've done so far. Somebody may come up with some other experiment, but that's the one that's done so far. So this is a rough idea of, or some artist description of what the microscope satellite looked like going around the Earth when those measurements were done. All right, there's another hypothesis in GR, which is called the geodesic hypothesis. In order to understand where this came from, you have to, of course, think about the fact that if the two are actually equal, then obviously all objects anywhere in a gravitational field would experience the same acceleration. Thus, all objects would follow the same trajectory if launched with the same position and same initial velocity, even if they differ in mass or other characteristics. It's as if the trajectory were determined by the space rather than what is being created by the forces. And so if you realize that everything's going to go through the same trajectory, then it could just be a function of space. So how can empty space determine a trajectory? Well, between 2 points in a well-defined mathematical space, there's a unique path, which is called a geodesic. And that represents the straightest possible path between those 2 points. Or equivalently, the path having the shortest, the longest path length between those points. It's a so there's an interesting book called When Something is Best. When length is, it has a whole book about this whole approach to doing things. Anyway, if you were to take a look at a two-dimensional space with a flat piece of paper, the geodesics are what we all know from Euclidean geometry, simply straight lines. So if you're in a surface like a globe, the geodesics are great circles. And for some reason, size of this is way too. Okay. So in a two-dimensional plane, you have a straight line. In the surface of a globe, it's called a great circle. But that's actually a straight line in flat space. If you were to take a cylinder that was tangent to the great circle, and then if you took that image along going around the cylinder, and then you unwrap that cylinder, a cylinder is a flat space, a two-dimensional flat space. So you would find that this is a straight line on that cylinder when you unwrapped it into flat space. So that's one of the ways which we'll eventually look at how geodesics are formed. And that's related to what's called a connection. Anyway, so this is a two-dimensional straight line and a globe with a great circle on it. I should have done this before I started the class anyway. Next time I'll look through before I go, simply leaving it the way it was. I apologize for all the corrections I'm doing. So in a two-dimensional space, you can form a surface of any convex object or a non-convex object. So for here, we have a potato chip surface, and you can, if you take a look at where the lines are here, it turns out they're all straight lines. You can actually draw straight lines on the surface of this potato chip. So for even a object like this, you can still have straight line geodesics. So you have to be careful when you're thinking about these things. Now, the geodesic hypothesis in GR asserts simply that a free particle follows a geodesic in spacetime. The idea of a free particle is one that is free of non-gravitational interactions. No charge, no electromagnetic interactions, nothing is happening except gravitational interactions. And according to this hypothesis, the gravitational field shapes the space-time, which in turn specifies the geodesics that the particle must follow. So the geodesic hypothesis only makes sense in a space-time, not in a three-dimensional space. We've been taking a look at pictures of everything in a Euclidean space in the pictures that we've been looking at. So let's take a look and do a little calculation to figure out what some things might look like. In Newtonian calculations or classical mechanics and in GR. So let's take a ball thrown. It, of course, will follow a parabolic trajectory from point A to point B in space near the Earth's surface. This is just a constant acceleration according to Galileo. So the other thing we could do, we could also fire a bullet that went through A and went through B. Because of its much greater speed, a bullet would have a much shallower parabola. But the definition of a geodesic implies that there should be a unique geodesic between points A and B. Therefore, the ball and the bullet, even though they're not interacting with anything other than gravity, they can't be following a geodesic in Newtonian relative gravity. Next time I will go through these slides. Okay. Um, so we can have the ball thrown high and slow, and it'll come down at B. We can shoot a bullet, and this is not to scale. If I did use it to scale, it would just be a straight line going back here for the accuracy of the picture. But the idea is that you would go at a much higher speed, and the height of the parabola here, well, the maximum point here is 5 meters, shown here. The height of this is 0.5 millimeters. So, as I said, it's a very small parabola. Now, so this is the classical take a look at what is going on. But in space-time, in GR, they're not the same ending points B and B prime, because the points in space-time have X, T, and Z. They have 3 coordinates, not just 2, as shown in the previous picture. So we know we're going to use A to be 0, 0, 0. And if B is the end of the bullet, then the X is 10 meters, Z is 0 meters, T is 1/50th of a second, which is about 5.99585 times 10 to the 6th meters. Everybody know why you can measure time in meters?
Yeah.
Okay. All right. Now, so B is this collection of numbers. B prime is the other end of the trajectory. So X is still 10 meters. They both went the same distance, but the ball went 2 seconds instead of 1/50th of a second, which is about a little over 1.5 billion meters. Z is still 0. So we have these 2 points, B and B prime, and we have A, which is 0, 0, 0. You can fit 3 points in a sphere or a circle. And if you do that, you'll find that the radius of curvature of that circle is about 0.05 light years in length. So the radius of that circle is order of 1 light year. Anyone want to tell me why it should be on the order of 1 light year? Not you, Stephen.
Okay.
Anybody else? All right, Stephen, you can answer.
I'll let you go ahead.
Pardon?
You go ahead.
All right. Well, we did it last uh, lecture when we did the the thing that in 1909 Einstein discovered that if you let the speed of light be a function of position, then you have a Minkowski space, and you get Newtonian gravity out of that metric. So the reason that you're going to have order of a light year radius of curvature is due to the fact that you're using a Minkowski space, not you're using a very limited version of GR when you're using Newtonian gravity. And so the dominant distances are all going to be the times multiplied by the speed of light. So that's why you're going to get a curvature that's order of 1 light year. No, that was the question. Sorry. So although the paths of the ball and bullet are clearly different geodesic paths when plotted in space-time, if we measure time in meters, then the calculation shows that both geodesics share a common curvature, and that you can think of it plausibly from just getting from the space-time around the Earth. All right, now we'll go to the question of why gravitational mass is inertial mass. And this is, of course, the weak equivalence principle. If we accept the geodesic hypothesis, then there's no distinction between gravitational and inertial mass. Near the Earth's surface, the geodesic for an object released from rest accelerates downward at a rate of 9.8 meters per second squared. And according to a geodesic hypothesis, this is the natural path for any free object to follow, analogous to a straight line geodesic, which we would naturally follow in deep space. Now, in deep space, accelerating an object away from a straight line requires one to exert a force on the object. And analogously, if I hold an object that rests near the Earth, it must exert an upward force on the object to accelerate it at the rate of 9.8 meters per second squared relative to the downward geodesic that it naturally wants to follow if you're sitting on a chair on the Earth. So the magnitude of the force required, according to Newton's second law, is simply mi times g, where mi is the inertial mass. So here's an apple. Oh, again, sorry. Okay, so here's an apple at Earth falling at g, and if you were in free space, you could have a rocket moving the apple up at the same acceleration that you get from gravity. So it is precisely the fact that you could use the same, well, if you were using a scale, then you could measure or weigh an object. And in classical mechanics, we imagine this upward force to be balanced by an equal and opposite magnitude to a gravitational force, m sub g times g, acting on the object. And we would imagine that the scale registers the object's weight, which after division by g gives the object's gravitational mass or inertial mass, which we're assuming are the same. But the perspective of GR, the only real force acting on the object, is the upward force. The one from around the Earth is simply a distortion in the metric, which makes the the speed of light be a function of position. So in GR, the only real force is the upward force that you have for holding it. The net force, which is required to accelerate an object relative to its geodesic. And that has a magnitude of m sub I g, and therefore we're measuring the object's gravitational mass using a scale. We're really measuring its resistance to acceleration. So of course in GR, m sub g equals m sub I. They're really the same thing. Okay. Inertial and non-inertial reference frames. Let's have a little discussion about those frames, which are obviously very important in both SR and GR. So in what we talked about a little bit previously, it means that in GR we consider an object's weight to be fictitious, not real, because the geodesic hypothesis says this is just a function of space-time. So we have to rethink the definition of an inertial and a non-inertial reference frame. In classical mechanics, we define an inertial reference frame to be a frame in which a free object initially at rest remains at rest. So if there's no exterior forces, electromagnetic, whatever other forces there are, if you were in an inertial reference frame, just let it go, it would remain exactly the same place. However, we can discard this definition when we treat a reference frame at rest at the Earth's surface as being approximately inertial. Obviously, a free object initially at rest does not remain at rest, but rather accelerates downward at g. So the Newtonian explanation, of course, is that Oh, okay. The object near the Earth's surface is not free, but subject to a gravitational force exerted by the Earth, and that's why it accelerates. However, the only evidence for this quote force unquote is the observed acceleration of a dropped object, which is only unnatural if we assume that the reference frame at rest at the Earth's surface is inertial. So we've got a built-in contradiction. Okay, that's not going to work. Sorry. Consider a object accelerated in free space, and we've got a box with a light source at the top and a detector at the bottom, and we're using a rocket to move it at the acceleration of g. So let's take a look at this situation. So as I've said, we've got a light of a certain frequency emitted from a source attached to the ceiling of the frame at rest on the surface of the Earth. This light is detected and its frequency measured by a detector on the floor of the lab. In such a frame, if it were really inertial in contradiction to general relativity, then the detected light will be observed to have the same frequency as the emitted light. In such a frame, though it's non-inertial as required by the equivalence principle. On the other hand, when you measure it from the point of view of GR, the light will be observed to be slightly blue shifted. The equivalence principle requires that what we observe, or the observer in a frame at rest near the Earth's surface, should be the same as what we observe in an accelerating frame in deep space, the previous picture that I didn't get to the right size. Okay. If you are imagining such an accelerating frame, and you are comparing it to a floating inertial reference frame, that is one with no acceleration, you're in free fall, then the photon emitted by the accelerating frame's ceiling source, that photon, if you were in the free falling frame, that photon's frequency would remain constant. But by the time T2 at the bottom of where the detector is, when it reaches that on the floor of the accelerating frame is moving upward at a speed of v equals gt prime. Therefore, in the floating IR, not having that velocity, the detector at the time is moving with a speed towards the source.
Therefore, the detector will observe the light in the moving frame to be slightly Doppler shifted towards the blue. And this shift will be very small because the time it takes to go in a very small distance in an accelerated frame will be very small.
That was measured by the Pound-Repka experiment, if I recall.
That was the first one, yeah. So the effect is so small that it took more than 50 years after Einstein first predicted it. But it was in 1959 that Pound and Repka were able to verify this effect by having a 22.5 meter high tower in Jefferson Physics Laboratory at Harvard University. And they used gamma rays from a radioactive sample of iron as a source and took advantage of the Mossbauer effect to make a very precise measurement of the frequency shift in the gamma rays as they were absorbed by a different iron sample at the other end of the tower. So Pound and Repka verified the predicted blue shift to an uncertainty of about 10%. Subsequent experiments verified in the Earth-based frame were later found to be about 1 part in 10 to the 4th. Tests of Einstein's gravitational redshift and blue shift theory have been verified to tremendous precision. Oh man. Sorry. All right, we'll do this over. We'll roll up. So at UC Berkeley, they used quantum mechanics because particles like atoms have waves. And so you can take ultra cold cesium atoms separated by a vertical distance of 0.1 millimeter, and using interferometry, you can get that the shift in the wavelengths of those atoms confirms Einstein's theory to 0.0002%, about 2 parts in 10 to the -6. There's miniature atomic arrays that have been developed after that, where the scale is not millimeters, but centimeters, and the fractional frequency gradient was an accuracy to about 1 part in 10 to the 19th per centimeter. So even better, there was also Gravity Probe A maser clock was launched into space and confirmed the gravitational redshift to, this was relatively early, and it was only 0.007%, comparing to an identical clock on a ground-based reference clock. The height between the two satellites was about 10,000 kilometers. And these are the papers So on the gravitational, this is the first atomic interferometry that was done. This is one of the more accurate ones done. This was done in 2010. This is 2023. And there's an interesting history of all of these different things in the history and philosophy of science. And there's also a book that I use for many references for various things about gravity tests called Recent Progress on Gravity Tests. This was edited by the Cardenas Abandonado, whatever. Anyway, so there's a number of references for these kinds of things if you're interested in looking at. So we see that the experimental evidence that we've done firmly supports the conclusions that the frames at rest at the Earth's surface are not inertial, and consequently, that freely falling frames are inertial. That is what we mean by the force of gravity. It appears to press us to the floor at the frame near the Earth is really a fictitious force, as fictitious as the force that appears to press us in a frame accelerating upward. Indeed, if it was truly inertial, freely falling, the objects would be weightless and none of the effects would appear. Okay. We're gonna have this problem again. Okay. Oops, a little bit more. Oh. Okay. Did the size of that a little bit bad. All right. So does that mean that gravity is entirely fictitious? If there's nothing about gravity that is real, that is observable in an inertial frame, then you would have to say that gravity is fictitious. But the answer to that is no. Gravity is real and does have an aspect observable in an inertial frame, in a freely falling frame, and in a non-inertial frame as well. It's just not the downward force that we usually consider gravity. To see this, we need to consider a large room freely falling towards the Earth. So here is a box freely falling to the center of the Earth, and there are 4 balls located in this here. Now, if you imagine those 4 balls floating initially at rest with respect to the room, there will be differences in the gravitational acceleration. There'll be acceleration from this, and this, causing this to go this way. There'll be one or these three that will cause it to go that way. This one's a little higher, so the net acceleration will be, there will be a difference in acceleration from down here that causes this to go up and this to go down. If you're floating in free space, in deep space, obviously they're just going to sit there. They're not going to move at all. So if we use the classical prediction, and the prediction will be correct even if it's not the proper interpretation. In that picture, the room's center of mass falls towards the Earth with a certain acceleration. The ball near the ceiling is just a little bit further from the Earth's center, and so it experiences a slightly smaller acceleration, just as the ball near the floor experiences a slightly larger acceleration. The balls near the walls accelerate towards the Earth's center, and thus along the lines. Okay. So this is the acceleration of these particles, and these, of course, are going on this line. Okay. So the balls are going to accelerate slightly inward from the ones near the center, while the one at the top is going to move up and the one at the bottom is going to move down relative to the center of mass. So if you were in a frame floating in deep space, the balls would not move at all. They just remain strictly at rest. So the relative accelerations of the off-center free bodies are something that even Newton knew about, and these are called tidal forces. So and this effect explains the tides on the Earth's surface. If we consider the Earth to be a frame freely falling in the moon's gravitational field, like the balls in our freely falling room, ocean waters on the sides of the Earth closest to and far from the moon will have different accelerations relative to the center, the Earth's center, and as bulge outward. So the other area, the sides will press inward, and this explains the 12-hour tidal variation at the depth of the ocean. Okay. So the last thing we have to think about is that space-time is curved. And physicist John Archibald Wheeler famously summarized the core premise of GR in his famous statement, space-time tells matter how to move, matter tells space-time how to curve. Wheeler's rephrasing of the theory translates the mathematics that we're going to learn in Einstein's field equations, and he simplifies it to matter tells space-time how to curve. Any object with mass or energy distorts the geometry of the four-dimensional space-time around it. And space-time tells matter how to move. Objects moving through this space-time will follow natural curves, geodesics, created by the mass around it. And we experience this as gravity. So, in order to understand these in mathematical terms, we have to understand differential geometry. And that's going to be our next step. We're going to do it twice. We're going to do Riemann geometry first. I did this in the wrong order here. This is internal geometry or interior geometry. And then we're going to do it a second time using Cartan geometry, which is exterior geometry. So I think in order to understand Cartan geometry, you need to understand Grassmann algebra, Lie groups, and a bunch of other stuff. So we're going to do the easier part, Riemannian geometry first. And that's what I'm going to start at our next lecture. Any questions?
Yeah, this is very interesting, Bob. I just want to point out you can arrange mass in a way that you can get a gravitational field without the tidal effects. If instead of having it as a collection, like in a sphere, if you arrange it into a very large plane, a plate, then it's like a parallel plate capacitor. And if you get close to it, the field lines are uniform, they're parallel.
Yeah, there's a lot of the analogy between electromagnetism and GR, although electromagnetism is linear and GR is nonlinear, so there are other effects that occur that you wouldn't see normally. So anyway, any other questions? Well, that's all I got this week. Like I said, this is just the introduction, and we're going to start on geometry next time. And because it's a little easier, we're going to do Riemannian geometry first, and then we'll do it again using Cartan geometry. And I'm not sure that I'll ever be able to get it to Simon's geometry, but that would be my goal, although I don't think I'm going to get there. And then we'll find, once we have the math of the geometry, then we can go relatively quickly. We can go through GR. So next step is geometry.
Thank you.
Thank you.
Okay. Well, unless there's, oh, I'm sorry, I need to stop. Cancel that. Let's stop the